Hello, my name is Niraj Bhakta and I work in Dr. Shug's lab here at UTA within the Chemistry and Biochemistry department. I will be presenting the work I've recently done on the characterization of a soft ionization by chemical reaction in transfer ion source hyphenated with supercritical fluid chromatography tandem mass spectrometry. What that means is we are using a commercially available DBDI source, which is a dielectric barrier discharge ionization source, coupled to a supercritical fluid chromatography, so a separation system, which then uses a mass spectrometer to detect analytes of interest. Now, why this is critical or important is this is the first time we're actually coupling a DBDI source with supercritical fluid chromatography. The unique aspect of this is the ability of this DBDI source to handle nonpolar analytes and to have a similar dynamic range as typical API or atmospheric pressure ionization sources. Another key benefit of this is supercritical fluids used in this chromatography separation are a green technology, which means there are low costs, less impact on the environment, and also less toxic reagents which are used by the analyst or the scientist during these separations. SFC also has a very high diffusivity and a low viscosity. I'll get into that, how that applies in just a second. As you can see in figure 1, the left is a typical API source. This is electrospray ionization, where we spray into the source, generate those ions, and then they go into the mass spectrometer to be detected. On the right side, we actually have that DBDI source, or the secret source, which generates the ions that then go into the mass spectrometer. So what we're doing is we're really making the generation and the transfer more efficient from the supercritical fluid chromatography into the mass spectrometer. What we did was we tested some reference standards from Sigma Aldrich. So we used typical SFC markers such as caffeine, theophylline, testosterone, theobromine, and uracil, and created a linear range. We started at 10,000 nanograms per mil and serially diluted down to 10 nanograms per mil. We injected these samples in quadruplet, so 5x, just to ensure we have reproducibility with the system. As you can see in figure 2, we have a very high correlation, so we have a very high expected to peak area relationship for all of the analytes. So if we draw a line, we expect any concentration to fall in that within 0.99 R squared, or correlation of coefficient. We also did some further tests with figure 3, so changing the methanol concentration from 5% to 10% to 20% to 30 to 40. So we're really increasing the amount of the methanol, which is a toxic reagent used in most separatory techniques. As you can see, as we increase the amount of methanol, we actually decrease peak area. Now, what is peak area? Peak area is the amount under the curve. So if we take a look at figure 4, which is in the top right, we see that if we have kind of a apex and going down the slope, we kind of measure everything within that and determine that to be the peak area. So that gives us the reliability of everything within that detector hitting and seeing this compound, that what we're seeing is true and is accurate. As you can see, as we increase the flow rate, we actually get a sharper peak. When we get a sharper peak, we get more peak area because it's not as diffused, it's not as broad. Also, another positive of this is we can get our analyte, or in this case testosterone, to come out within 2 minutes as opposed to running it at 1 mil per minute, and it's coming out just outside of 8 minutes. This is the first time this is being done for a SFC-MS, and further studies could also enhance nonpolar compounds, which are typically harder to ionize in this API source. Thank you.